All right, can you all hear me okay? All right. So what I want to do is first, basically I want to talk about the multimeter quiz lab. You can call it quiz or lab, whatever you want to call it. I got a lot of emails yesterday regarding difficulty in uploading the labs. I understand it. Don't worry if it was a little late. That's okay. I mean, I know some of the labs some of those files take a long time to upload, especially on YouTube. My lectures, my 1.5 hour lectures take probably 7 hours to completely upload onto YouTube. So that's fine. I understand that. You guys are one of the first groups where we're doing the video lab report. So still trying to iron things out. So don't worry about it if the file got uploaded late. Okay. I do think uploading the files to YouTube is probably the best thing to do because if you have to upload files onto Canvas, I think these files are way too big. Do you guys have any questions? Any questions, concerns, anything? So, someone had asked in the previous class what they need to do for the multimeter lab quiz, what are we going to call it? Let me switch. Let me get the file. So, maximize this. Sorry, too many windows open. Okay, so I have it due on the 30th. I can always add a couple of days to it. I mean, for some people who played around with circuits before, this is actually a pretty straightforward thing to do. But for people who've never done anything with circuits before, it might look kind of intimidating, but really isn't. Once you understand, it's like, oh, that's not that bad. So right now it's doing a week, but we'll see how it goes. I might make it through Friday, next Friday. They're the same thing. Basically, you're going to show me that you know how to wire the circuit up, wire circuit, how to use the multimeter. I just call them by different names. It's a quiz, skill demonstration, whatever. They're synonymous for me. So this is the document, and what you want to do is to film yourself carrying out the 6 steps shown. Let me magnify that. That's too much. Okay, so you just got to film yourself going through these steps. And I'm hoping that if you have a camera where you can pause it instead of stop and creating a new video, that'd be great. Because if you can pause the video, then you can go on to the next steps and then start the video again. Otherwise, you have to submit several files at once. So, like the first one, all you got to do is connect the lamps in series and the bulb in parallel. I gave away the answer already for the 2 questions, but and then number 2, you have to reverse. Basically, you have to have the bulbs in parallel and the batteries in series. So you just got to show that you can do those. Okay, number 3, you just have to film yourself measuring the potential difference across a lamp or battery. And each one of these shouldn't take that long. Wiring that board is not very complicated to wire once you understand what you're doing. Tyler created a video. I sent you a link to the video that you can upload. That's on YouTube. It's 10 minutes. It goes through the details. He did a very nice job showing you how to use the multimeter. For me, it's very hard to show you how to use the multimeter during the lecture, as I'm lecturing to you. But I think the video does a nice job showing you directly what you need to do. So what Tyler did is he did not use this circuit you're wired. He used a different circuit to show you how you measure, how you put the meter across the device to measure voltage, and how you have to put the meter in series with the element to measure current. Okay. So there's 6 steps. So now this document, if you in your video you show how you basically show this document in the video, all filled out, then you don't have to submit this particular document. Okay. But if you don't fill it, if you don't show it filled out in the video, then you got to submit the document along with the video. Does that make sense? Yes, no? If you have questions about how to wire things, this is going to be one of those situations where you kind of need to, we would have to do some sort of Zoom meeting, because describing this via email is a heck of a challenge. I don't see how via email it will be hard, be easy to troubleshoot. It's not going to be easy to troubleshoot what you're doing without me seeing what you're doing. And so if you're having issues with any part of this lab, you would have to set up a meeting and you have to show me via screen share what you're doing. Okay. Or it doesn't have to be screen share, but by video, I need to see what you're doing. Okay. Then I can diagnose what you're doing wrong if you're having trouble. In the previous class, a student asked, what if I have my own multimeter? Can I use my own multimeter? Because one of the multimeters is not the most accurate one. If you have your own multimeter and you want to use it, go for it. Okay, not everybody has a multimeter. So, in fact, somebody else asked, why do we have 2 multimeters? Because the next lab, you're going to have to measure voltage and current simultaneously. That's why. So you guys don't have any questions or concerns? Okay. So let me close this. And what I want to do is really finish my discussion on chapter 27. Like last week I talked about the basic components of a circuit, which is part of chapter 27. I want to develop a model for electrons moving through a wire. And the model, just one second. The model that I want to use is called a Drude model. Drude model. And I'm going to just describe in a very simple terms of what's happening to electrons in a wire. I'm going to be ignoring quantum effects, so my model is very rudimentary, but it'll work for us. At least gives us an idea what's going on. If you want to be more precise, you have to include quantum physics, which we're not going to do that here. But before I do that, I kind of want to talk about electric current. I defined the electric current last week as I equals the number of charge carriers per unit volume times the charge of the charge carriers times the drift velocity times A. And this is basically the amount of charge per unit area per unit time. This is called the current density. And of course, this was for the case where the current density is constant throughout the volume, and the velocity vector v is perpendicular to the surface A. But what if that's not the case? What if v is not perpendicular to A? So I want to go through and show you a little bit more elegant formalism to relate I to A and really the current density J. And we're going to use some of the ideas that we use in the chapter on Gauss's law. Okay. In fact, I took a slide and copied it and put it into here. Okay. So let me proceed. And let me say that, if you have charge carriers moving with velocity v sub d in some region of space, and you want to find out the current through some sort of cross-sectional area, let's say a wire or whatever, and the velocity vector is not parallel to the normal to the area, then you got to remember that only the components of v sub d parallel to the normal to the surface will pass through that surface. So in order to calculate the amount of charge passing through the surface, you need to take the dot product of v sub d with the normal to the surface, and that'll give you the component of the velocity vector that pierces the surface. So I had a little slide last week. I want to focus on this one, not the other one, where we talk about a flow of particles through a pipe. So let's look at the flow of particles, a flow of charged particles in a wire. Let's focus on electrons in a wire. And I talked about the amount of volume of particles that goes through A1 and the volume of particles that go through A2. That's what I did in the discussion about a week ago on Gauss's law, maybe 2 weeks ago. I'm going to do the same discussion here, and this time instead of having water flowing through a pipe, we're going to talk about charges moving through a wire. So the math is the same. The volume of particles that pass through A1 basically is going to be the drift velocity through A1 times delta T times the number of charge carriers per unit volume times A1. If I want to know the total charge, then I have to multiply that by Q, the charge per carrier. If you go on the right-hand side and you want to look at the particles going through A2, the velocity vector, the drift velocity, is not perpendicular to the surface of A2, and so only the components of v sub d parallel to the normal will pass through. So you got to take the dot product of v2 with the normal to the surface. So that's the expression you see here. Now inside this volume, inside the wire, if there's no source or drain of charge, then V1 and V2 are going to be equal. The charge, and we're going to assume the charge density stays the same. And so this is going to be V sub. So then V1 equals V2 equals V sub d, drift velocity of the electrons. So we can replace these with these V's in these equations with V sub d's. And if there's no source or drain, the number of particles that go through A1 has got to be equal to the number of particles that go through A2. If you if you cancel out the delta T, what you end up getting is an expression that represents the charge per unit area per unit time that passes through a surface. That's the current density. Okay, that's the current density. One second. Let me go back to the board. Let me switch views here. So this guy here is the current density. The only thing I had here is different is that V was perpendicular to A. So if I write it like this, like this is the magnitude of the current density. Okay. That's your J. So we can write our current as an integral of the current density over the area. So, and I'm writing this in a formal way, but in general, J is parallel to n hat, and J is uniform over the area. And so generally, I'm going to write the current this way, but I can say that this is equal to J times A. But I want you to be aware that I can be written as the integral of J dot NdA. There's going to be some problems in chapter 29 and 30 where you have to consider that, where you actually have a current density that depends on the radius, for example. So what is the drift velocity? Good question. So the drift velocity is basically the velocity of the charge carriers as they go through, let's say, the wire or the medium. If you have a wire, and it's length L, and you take the time, you take L and divide it by the time it takes for the electrons to go through the distance L, that's the drift velocity. It's a small number. It's actually a small number. We're talking about centimeters per second. And the reason why it's a small number is because the electrons in a wire, for example, they're undergoing many collisions with atoms. So the electrons are just bouncing around in here. Now they can do all kinds of stuff. As a result, it takes a long time for the electron to go from one end of the wire to the next. So even though the velocity, the electron's moving very fast in between collisions, the time it takes to go from one end of the wire to another, it's actually quite long. It's actually a small number. But V sub D is called a drift velocity because really the velocities are drifting through the wire. Does that make sense, Marvin? Okay. All right, so let's talk now about the model of conduction. So when a light bulb is connected to a battery, the battery does work on the charge carriers, okay, the electrons, causing the electrons to move. And so the battery converts chemical energy into kinetic energy. The electrons go through the bulb, they collide with the atoms in the bulb, they lose energy. Then the electrical energy is converted into thermal energy. The filament in the bulb heats up, it gets hot enough, and then the bulb blows. The kinetic energy loss of the electrons basically increases the vibrational energy of the atoms in the conductor as they scatter off atoms. And vibrational energy, meaning kinetic and potential energy, if they increase, that means temperature is going to increase. And the reason why is because temperature is a measure of kinetic energy of particles. That's something you will learn in Physics 215 if you haven't had it. Or you might have seen it in chemistry too. Temperature is a measure of kinetic energy of the particles. So I want to develop this Drude model. It's not a full development, but it's enough for us to talk about what's happening when the electrons are moving through, for example, through a wire. I'm always going to go by that example because that's what we're going to focus on. You can kind of apply this to charge carriers and in electrolytic solutions, but we're not going to do that here. We're mainly going to be focusing on electric current in a wire. So I'm just going to focus on that. So let's say we have a wire. And we apply an electric field in the wire, and you do that by connecting it to a battery. So let's say the electric field this way. Let's say the electric field is uniform. Let's say the wire's length is L. So we know there's a potential difference because the electric field means you have a potential difference. I know then that E, the magnitude of E, is the magnitude of delta V over L. Our field is uniform. And really what I'm going to focus on is average values. I do know that as the electrons go through, they're going to be undergoing collisions from time to time. But
yeah, Professor, 1 second. Do you keep screen just still on the slideshow?
Oh, I'm sorry. Thank you. Okay. So anyway, I draw my picture. I apologize. I forgot that. So here's a wire of length L, and I've written down the electric field, which is delta V over L. And as the electrons go through the wire, the field is constant. The field is uniform. I do know that as the electrons go through here, they're going to be constantly slamming into atoms. Okay. But overall, the electrons are going to be forced to the right because of the electric field. Let's focus on that forced into that field. Well, and that force is going to be Q times Z to the MA. So A be Q E over M. And it's going to be a constant. So if I integrate this to get the velocity as a function of time, and that's a simple integral, you know from kinematics that V is going to be the initial velocity plus the acceleration times time. And generally what I do is I look at it, I want to look at average values, I don't look at the average velocity. So if I want to take averages, then this is going to be equal to the average of V naught plus Q E over N times T average. Well, this average is going to be weird, so I'm actually going to be looking at an average time. So let me write it in terms of an average time. What is the average of this? What is the average initial velocity? That's the question to ask. Well, the particles are going to be randomly oriented. Their velocity vectors initially are going to be randomly oriented. So on average, this thing is going to go to 0. And so this, the average, which is what we call the drift velocity, is going to be Q E over M. And this average time here, I'm going to denote by the Greek letter tau. And that Greek letter tau represents the average time between collisions. Okay? It's the average time between collisions. So then I can write J in terms of that quantity. Remember, J is N, Q, B sub B. The J is going to be N is Q, has this expression. And what you see is that J is equal to some constant times the electric field. We're going to denote that constant as sigma. Again, sigma is going to be written as N Q squared over M times tau. And we're going to call this the conductivity. I'll say a little bit more about the conductivity in a minute. Now, since I is J times A, then I can write the total current in the following manner. Remember, these are magnitudes. I'm assuming that the normal to the surface and J are parallel. So this will end up being N Q squared or M tau, and the E here is really the magnitude of the electric field. So that quantity, sigma, is called a conductivity, like I said. It's an amp volt per meter. In fact, sigma, the units, can be written as mole meters. There's other names, but one of them is mole meters. Mo is almost spelled backwards. Okay, you'll see where this comes from in a minute. Okay. If the ratio of J to E is a constant independent of the applied electric field, then you obey Ohm's law. This is really where V equals IR comes from. If that ratio is independent of the electric field and constant, then the material obeys Ohm's law. Ohm's law is like Hooke's law because it's only really valid for a range of E's, because if you make E too big, the material will heat up, its resistance will change, its conductivity will change. So although this allows us to define what resistance is, it's not going to say anything about, not going to say enough about what that term means, what does it depend on. That term is really going to require us to know quantum physics. Okay, what that value of that term and what does it depend on. Okay. We need quantum physics to understand. This is a property of a material. And if you notice, these numbers, especially this one, it's all going to be dependent on the material, the average time between collisions. Well, it depends on how densely packed the atoms are. All right, so this is all going to be dependent on the material. Okay, let's continue. So, since the electric potential, is E times L, and I'm keeping everything as a positive number, so those all represent magnitudes, like I got rid of the minus signs. Because when we're dealing with these circuits, we're looking at absolute values of the quantities. So since delta V is equal to E times the length of the wire, and then J, current density, which is sigma times Z, can be written as sigma and V, delta V, over L. Which means that delta V can be written as, well, L times J over sigma. But if I is J times A, then J is I over A. So I get that delta V is some constant times the current. This thing in brackets is the resistance. So this L over sigma A is the resistance. I basically rewritten Ohm's law. I went from here to here. It's Ohm's law. Okay, so if this number is a constant independent of the applied voltage, then the material obeys Ohm's law. Does that make sense? And we see that resistance depends on the length of the wire and 1 over the area of the wire. And this constant that depends on the properties of material. Now we can rewrite sigma. We can define rho equals 1 over sigma. We call that the resistivity. And so we can write this as rho L over A. And again, that's our resistance. And this equation works. This equation is valid as long as A stays constant. If I have a wire, a strange wire, whose area increases linearly, for example, along the length, then in order to calculate R for this, you have to take into account the change in the radius as a function of length. And so to calculate R, you would actually have to do an integral. You'd have to actually find an equation for dr and express your A in terms of the length of the wire. To calculate, so to calculate R. So this is another quantity, resistance, that depends on geometry. And if you get a wireless like this, which is rare, calculating it is tough. Of course, engineering books tabulate all these things. We don't spend a lot of time calculating resistance as a function of real geometries. There's one or two problems in the book. Okay. Any questions so far? Oh, by the way, what are the units of resistivity? Ohm, meters. Sigma is mole meters because they're reciprocal of each other, so what we decided is to just put the letters in ohm. Get a new unit. Connectivity is used in other fields. I mean, it's used in looking at the properties of conductors. Okay, but you see in other fields when you talk about thermal conduction, or maybe in terms of fluid flow, or gas flow in a pipe. Mechanical engineers use this quantity. Mathematically, the same ideas. And so the unit for the resistance is the ohm, which is a volt per amp. Fairly small unit. Typically resistances are like 1,000 ohms. 1,000 ohm means a kilo ohm. 1,000,000 ohm is a mega ohm. You use the capital Greek letter sigma to denote the ohm. Instead of writing out the whole word ohm, you write the capital letter omega, which is you see on the screen. The value for the resistivity, the typical values are tabulated. I don't expect you to memorize them. Typical values for the resistivity for a conductor, they're like 10 to the minus 8 ohm meters. And for insulators, it's about 10 to the 10. If we're talking about ideal conductors, rho should be 0. If you're talking about ideal insulators, rho should be infinity. But real conductors, rho is around 10 to the minus 8. And for real insulators, rho is about 10 to the plus 10. Okay. Questions? So one of the things, and I'll go through this quickly, one of the things the Drude model doesn't take into account is the fact that this guy, the conductivity, and this guy depend linearly on temperature, over a temperature range. And we can see that because we're not taking quantum mechanics into account with this model. What this model does allow us to see is the relationship between V and I. But to actually say something about rho, you need quantum physics to actually get a better handle of what it depends on. And to say that this would depend on, to say that rho or sigma depends on temperature, what that means is that rho or sigma have to depend on velocity squared, because temperature is the average. Temperature is a measure of the average kinetic energy of particles. If one does an experiment, one can show that the resistivity rho depends linearly upon temperature over a short temperature range. So we can say rho depends linearly, and so it's given by that function. If you want to know this over a large range, you have to do an experiment and measure it and plot the graph. Rho naught and T naught. Rho naught is the value of the resistivity at 20 degrees Celsius. Generally, that's taken as the reference point at 20 degrees Celsius. We're not going to do a lot of problems where we're looking at rho as a function of temperature. We'll see one in the homework. But if you're taking the materials course, if you're an engineer, it will be important to you. I just want you to be aware that this relationship is linear for small temperature range. Otherwise, the other way is not. You're going to see that with the light bulb. When we do Ohm's law lab, you see it because when the light bulb gets hot, its temperature increases, and you'll see how the resistance varies. Since R is equal to rho L over A, then it must be true since R is proportional to rho, R has to be equal to R naught, 1 plus alpha T minus T naught. And again, alpha is the coefficient of resistivity. It has units of 1 over Celsius. typical values of the order 10 to the minus 3. If you wanted to solve this equation for alpha, then alpha would end up being 1 over rho times delta rho over delta t. And that's an average alpha. If you want the instantaneous value of alpha at a temperature T, you have to take the derivative of rho with respect to temperature at a particular point on the rho temperature curve. If we can plot rho as a function of temperature accurately, then for a material, then we can use that material to make a thermometer. It's called a thermistor. Again, remember, a conducting device obeys Ohm's law when the resistance of the device is independent of the magnitude and polarity of the applied potential difference. Resistance is defined to be delta V over I. Now, for a light bulb that's not ohmic, you can still define R to be delta V over I, just that R is not constant. What people forget is the resistance is independent of the magnitude of the polarity when it comes to Ohm's law. That's the key. Let me ask you a question. Suppose I have a wire that obeys Ohm's law. And I have 3 amps going through the wire. Suppose I double the current in the wire. What happens to the resistance? I double the current in the wire, what happens to the resistance? Remember, it's a material that obeys Ohm's law. Right? R is delta V over I. The fact that I doubled the 6 amps means that I double the voltage. You'll always see questions like that, weird questions like that to test your understanding of the definition of Ohm's law. Remember, resistance is independent of the applied polarity and magnitude of the potential. I did double the current, but in order for me to double current, I have to double the voltage if it obeys Ohm's law. Right, because I said this is a wire that obeys Ohm's law. I see this question a lot in like tests and stuff. Okay. You look at the conceptual questions, and I asked one for this unit, I asked one just like that. So yeah, both have to get doubled. You're right. I didn't specifically say that. But the key is understanding that a wire obeyed Ohm's law. But it's a typical question that's asked. I'll say that. Okay, and it gets a lot of people. Okay. So one last thing, and then I'll do an example. Because batteries convert chemical energy into kinetic energy, power supplies produce electrical energy too. We want to look at the rate at which energy is dissipated in a circuit. Because when you have electrons going through a circuit, those electrons are going to be dumping their energy into the atoms in the wire, causing wires to heat up. All the electrical energy eventually gets converted to thermal energy. I mean, if you ever use a heavy electrical equipment, even a vacuum cleaner or a heavy drill, You run them for a while, you'll feel that the wire that goes to the plug gets warm. Because they're running a lot of current, they're producing a lot of heat. A lot of energy is being, a lot of the electrical energy is being converted to thermal energy. Okay. So what happens is the work that was done by the battery to give potential energy to the system decreases as charge goes through a resistor. So we can define the rate at which energy is dissipated as, you can say, as delta U over delta T, or dW dt, however you want to write it. And I'm writing this in my slide in very simple terms. Delta U is just Q, delta Q, delta V. And the whole thing's divided by time. And I write delta Q because I'm looking at a small amount of charge that passes through in a certain time period. The delta Q or delta T is current. So power is I times V. I want you to understand that the concept, the idea of power is a defined thing, right? Power is defined to be dW over dt or du over dt, however you want to look at it. W is the work done by the battery, for example. Okay. This is a defined quantity. But if you use the principles of circuitry, that quantity is delta V times I for electrical circuits. If you use Ohm's law, you can rewrite the expression for power two other ways. I'll let you figure that out. It's not hard. All you got to do is, if you solve this for I, stick it in here, you get that. If you solve, if you take I times R, stick it in here, you get this guy. But either way, the power equation, however form it is, it's based on a definition. You will see people who are not in physics call the power equation a law. It's not. Okay? You'll actually see books on electricity, not physics books. Books in other fields where they teach people how to wire circuits. They call that Watt's law. Okay. Watt was dead 9 years before the laws of electricity were developed. Okay. Watt had nothing to do with it, but you'll see some people call it Watt's law. If you go online and you type Watt's law, you'll see worksheets on Watt's law. Yeah, I tell you that because there's a lot of people who are taught this, and they don't think they're wrong about it, but they are. All right. So that's how you calculate power. So I want to ask a question regarding power. Suppose we have two light bulbs. One light bulb is 25 watts and the other light bulb is 100 watts. Which bulb has a greater resistance? What do you think? Well, you got to remember, a light bulb is rated at a voltage. Light bulbs are rated at 120 volts. So that 100 watt or that 25 watt assumes you're applying 120 volts to the bulb. So having said that, can you answer the question now? Which bulb has a greater resistance? And what you have to do is look at power in this form. Both bulbs will have 120 volts across them. bigger P has a smaller R. So the 25 watt bulb has a higher resistance. And has less current going through it. I'm going to ask a lot of fun. I'm going to ask them some fun questions later on involving bulbs and series in parallel. Okay, we'll have fun with it. I'll do a demo and ask you some questions. I'll try to make it interactive. Okay. So one last thing, I just want to do a pretty basic example, and I'm pretty. I'll pretty much be done with chapter 27. Like I said, there's not a lot in chapter 27, just the basics of circuit. Some books don't even have a separate chapter on Ohm's law. So I kind of covered it at a rudimentary level. At least I think so. So let me draw the circuit. I have basically a battery or a power supply, whatever you want to call it, connected to a 45 ohm resistor. And I'll bring examples of resistors when we're focusing on circuits more later on. So we have a 45 ohm resistor and a 9 volt battery. And I have an ammeter too. Here's my resistor, it's a symbol for the resistor. Here's the ammeter. I draw a circle. The ammeter is in series with the resistor. That's the only way I can measure. That's the only way I can measure current correctly. So I want to calculate current. I want to calculate power, energy used, etc. Okay, let me find another color marker. Marker. Okay, so I will go with the blue marker still. So current can be determined from Ohm's law. Delta V is I times R, so I is delta V over R. Delta V is the 9 volts across the battery, which is also that across the resistor, divided by 45 ohms. This is 0.2 ohms. Or 200 millivolts. Anything strange about what I'm doing right now? You notice I'm ignoring the fact that the ammeter is in a circuit, right? I'm completely ignoring the ammeter that's in the circuit. I'm assuming that the ammeter doesn't affect the circuit when they set that up. So the ammeter has to be designed so that it doesn't affect the circuit. Yeah, you're right. The ammeter is negligible resistance. Its resistance is small compared to that of the resistor. That's not always the case. You can find yourself in a situation where the resistance and the ammeter are the same order as the resistor itself, then you're in trouble. I've actually encountered those situations. So what's the power? P is delta V times I. The delta V is 9 volts. I is 0.2 amps. 9 times 0.2 is 1.8 watts. Remember, and I forgot to mention that before, the unit of power is the watt, it's a joule per second. Another straightforward calculation. How much charge is delivered by the battery through the circuit? Well, I'm assuming constant current. If I'm assuming constant current, I can say I is delta Q over delta T. Otherwise, the deltas would be D's if I depended on time. Then delta Q is I delta T. And so in this case, it's going to be 0.20 amps, which is a coulomb per second, times 15 minutes. Ooh, how many seconds is that? 15 minutes times 60 seconds per minute. 15 times 60 is what, 900? 900 times 0.2 is the same thing as 900 divided by 5. 180 coulombs. Okay. What's the energy? What's the energy dissipated by the resistor in 15 minutes? So I know 15 times 60 is 900 seconds. I know that power is dW dt, so that the energy is power times time. I'm assuming P is constant, so all I got to do is multiply. If P varied with time, then this would be an integral. Okay, the power is 1.8 joules per second. The time is 900 seconds. That comes up to 1620 joules. But I want this in kilowatt hours. Yeah, I'm sorry, I didn't see that question, Pedro. In terms of the multimeter, you're going to put it on a scale where you want its resistance to be small compared to the rest of the circuit. Okay. So if you're measuring current, current actually has multiple settings on it. And sometimes there are two possible settings you can use with the multimeter. Ideally, you want the one with the lower resistance, which means you're measuring a higher current. But it's possible on your multimeter you might get less sig figs. So you got to figure out what would be the best for you. I mean, ideally, that's what you want to do. You want the smallest resistance. But if it's too small, you're not going to get enough sig figs. So it's going to depend on what you need, what your needs are. Okay, if you need an extra sig fig, then it's okay to have a slightly higher resistance. But when you're using the multimeter, when you're using like the 200 milliamp scale, on the one we have, and a 10 amp scale, the difference in resistance is not that much. It's when you go to the 200 microamp scale, then the resistance is like 1,000 ohms. Okay. I want to convert this to kilowatt hour. What the heck's a kilowatt hour? 1 kilowatt hour is the amount of energy used up in an hour. That's a kilowatt is 1,000 joules per second. How many seconds in an hour? 3,600 seconds. You multiply them two together. 1 kilowatt hour is 3.6 million joules. And so if you want to figure out how many kilowatt hours this is, you take 1620 and then divide it by 3.6 times 10 to the 6 joules per kilowatt hour. And you get your value. So, one of the things you can do, when you get your electric bill, you can see how many joules of energy you used up in a month. Now that you know how to do that calculation. Questions? No questions? As we go through this next slide, please again keep me informed on how the lab is going. I do envision this lab being harder because it's online. That's why I give you a little bit extra time. Like we're giving you extra time for all the labs. Usually I do 3 or 4 extra labs during the semester when we're on ground. And they're all written. So, like I said, all the stuff we're doing is brand new. So I need to know how it's going for you guys. Okay. And it's so difficult to show you things from here as opposed to being in class. So you just gotta provide videos for you. Questions? Concerns? Okay, so I guess I'll end it here. And next week I'm going to answer questions you may have on this exercise. I'll call it that. And then I'm going to start an Ohm's Law, the Ohm's Law lab. In the Ohm's Law lab, you're going to measure voltage and current, the resistor, voltage and current through a light bulb, and then the last one will be a diode. One element that obeys Ohm's law and 2 that don't. And again, the focus will really be on learning how to make the measurements and how to wire the circuits. That's really, to me, that's going to be the focus of the lab. But it'll be your first written lab. Okay. All right. I guess that's it then. If I don't see you, have a nice weekend. If I don't see you in the next class, have a nice weekend.